All right. Well, good morning, everyone, and thank you so much for joining us this morning. We have a great lineup of presenters for you all this morning, and I just want to thank you for taking the time to join us. And if you're not joining us live, I hope this recording is finding you well also. We are going to go ahead and get started here shortly, but I wanted to go over a couple things. Again, thank you for joining. This is going to be the first webinar of a series of three webinars centered around some of the companies that are going to be joined together for Pittcon 2025 as part of this ICP Alley initiative. So this week we have Liv Forbes from Inorganic Ventures, and then Ryan Brennan from Glass Expansion. And then we also have in the coming weeks, you're going to see some webinars from CEM and GFS Chemical. They're going to do some great webinars, and you'll get more information on those as they come out. But it should happen. I believe the next webinar is scheduled for February 13th. So keep an eye out for that. ICP Alley is going to be a little feature we're putting together for Pittcon this year, where those four groups will get together and be able to answer any questions that attendees might have in real time. So if you're at Pittcon this year, please stop by and see us at ICP Alley. Just some other housekeeping items before we get started. If you have a question, please use the Q&A box at the bottom of your screen. So if you look down at the bottom, there's a chat and a Q&A. So if you have a question, please use the Q&A box. It'll help us keep track of them. And all questions will be answered after the presentations. I think that about covers it. So I'm going to introduce our first speakers this morning, and that's going to be Ryan Brennan from Glass Expansion. And we also have a very special guest, Robyn Goacher from Materion, who's going to sort of jump in on Ryan's presentation, I believe towards the tail end of that. So I will hand it off to Ryan, who's going to start us up. And again, thank you so much for joining us this morning.
Thank you, everyone, for joining today. As Mike said, my name is Dr. Ryan Brennan, and I'm president of Glass Expansion, Inc. Today, I will be talking to you all about tips and tricks to improve signal stability in ICP-OES and ICP-MS. Before I get started, just a very brief introduction for those of you who are not familiar with Glass Expansion. Glass Expansion has been designing and manufacturing ICP sample introduction components for over 40 years. During that time, we have gained global recognition for quality and reliability of our product line. Our product line encompasses the entire sample introduction system for both ICP-OES and ICP-MS instrumentation, from the autosampler probe all the way to ICP-MS interface cones. We also offer very convenient tools and accessories to make life easier in the ICP laboratory. I also wanted to mention Glass Expansion's wealth of resources. From a customer standpoint, we have a fully equipped R&D lab with the latest ICP-OES and ICP-MS instrumentation. We have an expert technical staff to assist you, and on our website you can find a variety of different ICP resources, such as application notes, newsletters, ICP catalogs, product flyers, product care guidelines, as well as operating instructions, video assembly guides, and webinars like today's. Today, I'll be introducing a variety of different Glass Expansion products and accessories. These will be very brief, so if you're looking for any more in-depth understanding of those products, I encourage you to reach out to Glass Expansion and to visit our website and check out all of these ICP resources. Now on to today's topic. So signal drift in ICP-OES and ICP-MS is detrimental to every laboratory. Today, I'm going to try to cover some of these different factors that can affect the stability of your measurement, such as insufficient maintenance procedures, improper selection of sample introduction components, matrix matching, and touch a little bit on adjusting operating conditions based upon the sample matrices that you're dealing with. So to get started, let's cover some very basic general tips. So you want to optimize your instrument at the beginning of every day. So inspect the peristaltic pump tubing, replace that if it's worn, Check your blank readings before getting started. It's very important to have regular rinse protocols. Make sure that you're rinsing in between samples for a sufficient amount of time, and also at the end of each run. It's best to ensure that your rinse solution matches your sample matrix to conform with matrix matching. And you want to start and end your analysis by nebulizing that rinse solution, and follow by using ultra pure water rinse to make sure that that rinse solution is fully rinsed out. Now, with respect to regular maintenance, the frequency at which you're going to clean your instrument, replace components, are going to be somewhat dependent on how often your instrument is running and the types of samples that you're dealing with. But you want to make sure that you're cleaning your nebulizer, your spray chamber, and your torch regularly. Clean your cones as necessary, right? So we want to make sure that our cones are conditioned. So we don't want to clean them too often because that can also contribute to drift, and I'll touch on that a little bit as well. For ICP-OES, we want to make sure that we're cleaning our windows. For all instruments, we want to make sure that we're checking all the seals. Torches have O-rings on them that make airtight seals. You want to make sure that those are checked and regularly replaced. You want to follow your manufacturer cleaning and replacement interval guidelines. As I mentioned, our website is a great resource. We have a whole section dedicated to providing you with product care guidelines. To touch specifically on nebulizer tips, you want to, at the very beginning, after your instrument has warmed up, you want to check the back pressure of your nebulizer. So a tip: low back pressure is going to have a direct effect on the nebulization efficiency of your nebulizer. So you'll see a loss in sensitivity, you may see an increase in your precision or RSDs, as well as your long-term stability. So a low pressure is most likely going to indicate that you have a leak somewhere in the connection to your nebulizer or in the peristaltic pump tubing, because it's not delivering at that accurate flow rate or gas flow rate. A high back pressure is likely going to indicate that you have a partial clog somewhere in the system. So that's going to indicate that you need to clean or replace your nebulizer, your auto sampler probe, or check any of the capillary uptake pump tubing. Another important tool is to make sure that you are monitoring what your normal sample uptake rate is. Again, this is a good indicator of whether or not your peristaltic pump tubing is worn or needs to be replaced, or again, if you have a blockage somewhere in the system, a drop in sensitivity. Glass expansion has several different types of tools that are geared towards maintenance of your nebulizer, monitoring your sample uptake rate. That just makes it more convenient and easier for the lab analyst to check these things. Your spray chamber, tips for cleaning that: when you're using a glass or quartz spray chamber, it's very easy to notice when it's time to clean that spray chamber, because what you'll start to see is beading up on the walls of that spray chamber. That's a good indicator that the samples that you're analyzing, that matrix, has sort of built up a film on the sides of that spray chamber. That's going to contribute to drift as well, because you're basically you don't have a clean surface. The spray chamber itself is not going to efficiently clean out the previous sample when you're adding in that rinse between samples. So just make sure that, again, you're kind of monitoring that and clean it regularly. Follow your manufacturer guidelines. If you're dealing with inorganics, we find that Fluka RBS 25 is an excellent glassware cleaner. We recommend that you soak the spray chamber, remove all fittings, and soak it in about a 25% Fluka solution overnight, and just make sure that it's thoroughly rinsed and thoroughly dried with DI water before reinstalling it. You also have consumables on your spray chamber that are going to affect the nebulizer seal. Just make sure that you're checking the seal of your nebulizer within the spray chamber. You also want to make sure that you have very efficient drainage of the spray chamber. So a good indicator is looking at your waistline. You should see basically a steady stream of air bubbles. That's a good indicator that your spray chamber is draining efficiently. If it's not, you'll see big air gaps followed by big slugs of water. And what will happen is that can also contribute to drift because you're basically changing the pressure inside that spray chamber, and you're going to see your signal fluctuate with that. With regards to your torch, really the most components of your torch that you're going to have to clean regularly are the very end of the outer tube and the injector. Obviously, it's a lot easier to clean a demountable torch because you can take those components apart and you can get to the outer tube and the injector much easily compared to like a fixed single piece torch. Carbon deposits are most easily burnt off with a handheld torch or baked off in a furnace. Salt deposits, again, we recommend using Fluka RBS 25. Metals, those metallic films that are left around are most conveniently or efficiently rinsed off by using the same acid that you're using to digest those samples. So whatever in your matrix. Just one note for Glass Expansion's patented D-torch. The outer tube is completely removable, but it's held in place by a ferrule. You do not want to completely soak that in acid or put that in a furnace. So what we recommend is just turning the torch upside down and filling up a beaker with cleaning solution just to the point where the torch is exposed to those samples. For ICP-MS cones, I talked a little bit about you have to be careful with the frequency at which you clean your cones, right? Because it's really important that those cones prior to use are conditioned. So proper conditioning of your cones in ICP-MS is one of the most important factors of maintaining, that long-term stability and eliminating that signal drift. The other thing that you want to do, many cones, especially the sampler cone, use a gasket. That gasket is really important for making a proper seal and ensuring that that cone is properly cooled to an appropriate temperature so it's not running too hot. That leads to improved long-term stability as well as increasing the lifetime of that sampler cone. So gaskets, very, very low cost consumable item. Every time that you take that cone out to clean it or to replace that cone with a new one, you should be replacing that gasket. O-rings for certain ICP-MS instruments that have interface cones that have an O-ring with them, those can last a little bit longer than a gasket, but you still want to check them and make sure that there's no cracks and they're not brittle. Again, it's really important to make sure that you've got a good seal on those cones to make sure that you're improving your stability, eliminating that drift, but also improving the lifetime of those cones as well. Now, the first topic that we'll sort of talk about that can contribute to drift are blockages, right? So the most two common types of blockages we deal with are from undigested particulates or items in the laboratory environment that contaminate your samples, like dust or fibers. There can be fibers left over from your pre-sample filtering. And then the other type of blockages that we deal with is salting. Salting can build up on the interface, whether it's cones. It can also build up on the tip of your injector and your nebulizer, and that is going to contribute to significant drift of your signal. So here are some accessories or tools from Glass Expansion that you can help to eliminate particulate blockages. So Glass Expansion has a Guardian inline sample filter. This is a really convenient tool to safeguard your sample introduction system. It's completely inert. It's made out of PEEK. It is a reusable filter. It's most conveniently installed on the capillary tubing of your auto sampler probe. That way you're protecting everything, not just your nebulizer. You're protecting all of the capillary tubing. If you're using a a switching valve or a fast accessory, the inner components of that valve can be very troublesome for fibers or particulates, resulting in a blockage. What's nice about the Guardian inline filter is you install that before everything, so that you can capture any of those things that accidentally get taken up. Basically what you can do is you can very easily and conveniently troubleshoot your sample introduction system, because you will know where the blockage is immediately. You know that the filter has caught it. You can unscrew it. And with our LUO and an adapter, you can easily back flush that off. The filter itself can be sonicated. We recommend doing that like maybe every once a month. But daily, just a quick, easy back flush and install that back onto the capillary tubing, and you're good to go. Another new product that we just released that can help with particulate blockages as well as cross-contamination is our Guardian Auto Sampler Probe. So a very similar concept to the Guardian inline filter. At the very tip of the Guardian Auto Sampler Probe is an inbuilt frit. That frit does two things. It prevents undigested particulates from being taken up the auto sampler probe, but it also prevents dripping. So a lot of times with the standard PTFE encapsulated carbon fiber probes, you see a lot of droplet accumulation on the exterior of the probe, and as the probe moves from sample to sample, it will drip or scatter those droplets across your auto sampler sample vessels. That can result in cross-contamination. So the Guardian Auto Sampler Probe, like the Guardian inbuilt filter, is completely inert. It has a ceramic tip with a peak body, and then we have interchangeable UniFit sample lines to match what capillary tubing ID best fits your sample introduction system. Now, to minimize salting on your cones, your nebulizer, your injector, you want to use an argon humidifier. Glass Expansion's argon humidifier is our Allegra. We have two versions. We have a single channel with a bypass switch, and we have a dual channel argon humidifier that's most commonly used on ICP-MS instruments. It's a very simple concept. All we're doing here is we're filling the Allegra with deionized water, and we're humidifying the nebulizer gas. Adding that moisture to the nebulizer gas really helps to reduce or eliminate the buildup of salt deposits at the tip of the nebulizer and the tip of the injector. You'll utilize a dual argon humidifier when you want to humidify both the nebulizer gas as well as your option or your dilution gas. And like I said, that's most commonly seen on ICP-MS instruments. Another tip to kind of help improve long-term stability is you can increase the auxiliary argon flow to sort of move the plasma a little bit higher or further away from the tip of the injector, and then add in extended rinse times. Here's both I really like this picture because it shows you both analytically from an ICP-OES signal standpoint, and as well as visually what the benefits of an argon humidifier can do. So this is showing a study of measuring 3 different internal standard lines in a lithium metaborate fusion type method. So the customer struggled with instrument drift. As you can see, their analysis would fail, go out of range after about 35 minutes without an argon humidifier, which caused them to stop the instrument, clean everything, and rerun those samples. Obviously, that's a lot of wasted time for a high productivity testing laboratory that's costing them lots of money because they're not being efficient. So with the argon humidifier added, they were able to complete each of their sample sets, which were a little over than 4 hours. And then pictorially, I got these photos from our good friend at Inorganic Ventures, Madeline Ghazi. A lot of times Inorganic Ventures will do a stability analysis of their stock standards where they're running really highly concentrated certified reference materials for a stability analysis. The problem is that on Madeline's instrument at the time, the OPI interface of the Spectra instrument would rapidly build up with salt deposits, and that would result in a signal drift. So we sent Madeline an argon humidifier to see if we could pictorially capture this happening. And what you can see here is just the picture of the OPI interface without the Allegra after that same sample set run, and one with the Allegra. And you can see a significant reduction in the amount of salt deposits that are building up on that OPI interface. And you can expect to see the same type of results on your ICP-MS cones as well. An internal standard is commonly used in ICP-OES and ICP-MS to compensate for variations in sample uptake rates due to differences in viscosity or matrix matching or mass to space charge interferences in ICP-MS. Use of an internal standard really can greatly improve your long-term stability. Glass expansion has a very convenient tool, our Trident. We improved upon the legacy Trident design by introducing our constant torque Trident design, which basically just offered a zero dead volume, constant torque or ratchet type fittings to make it easy to assemble the Trident to give you better results and easier to install. Something that Robyn is going to talk to us all in great detail about in a few minutes is drift due to a change in the laboratory temperature. So this plot is just to show you a normalized signal intensity plotted against a change in spray chamber temperature. So what you can see is there's a 30% increase in the ICP-OES signal if you go from 25 to 35 degrees C, or on average about a 3% change per degree C. So if your laboratory struggles with maintaining a constant temperature, maybe it's different times of the year where it's the heat of the HVAC is working harder or the cooling efficiency is working harder, depending on the time of the year, you can see a significant drift in your instrument's signal intensity over that time. To combat drift due to temperature changes, Glass Expansion has a very convenient accessory. It's our ISOMIST XR temperature-controlled spray chamber. The ISOMIST has a variety of different applications, not just controlling drift, but what we'll sort of hone in on today is the advantage of maintaining the spray chamber at a constant set temperature. So as you can see in the plot down here, you get a significant improvement in that signal stability over time by just maintaining a constant temperature. And Robyn will talk a lot about her work at Materion and how she was able to utilize the ISOMIST to combat drift in her lab. As I introduced in the beginning of today's webinar, it's also important that you are selecting a proper sample introduction system to handle the types of samples that you're analyzing. Glass Expansion manufactures a variety of different nebulizer designs, each of which has a different tolerance to particulates, to chemical resistivity, to analytical performance goals. On our website, you can find some really convenient flowcharts that help you to select the best model to suit your application needs. With regards to operating conditions of the nebulizer, I really like this study. We recently acquired a aerosol diagnostic tool in our R&D laboratory. It's a great tool for designing new nebulizers, but it's also a great tool for sort of understanding how the operating conditions of your nebulizer affect its nebulization efficiency and how that nebulization efficiency affects your analytical measurements. So what we're seeing here is a plot of the percent volume that is less than 10 microns. So it's well known in our industry that in order for a plasma to completely vaporize, atomize, and ionize that aerosol, the size of those droplets should be 10 micron or less. So what we're showing here is the percent volume of a primary aerosol produced by a low flow concentric nebulizer. and what percentage of that is less than 10 micron. So as you can see, we're keeping the sample flow rate constant at about 0.4 mils per minute, and we're increasing that nebulizer gas flow rate. So as we're increasing that nebulizer gas flow rate, we're increasing the percentage of that volume of aerosol that is less than 10 micron. Now, what does that relate to with regards to the analytical measurements of, say, your ICP-MS? Well, as we increase the volume of that aerosol that's less than 10 micron, you can see that the signal intensity is increasing. But also at the same time, we have to be careful or cautious with ICP-MS because we're increasing the water vapor that is being, the volume of water vapor that's being introduced into the instrument. And as we know, that's going to increase our oxide ratio. So that's going to affect the robustness of our plasma. So if we're dealing with a really high matrix sample, we have to kind of tune our nebulizer such that we're meeting a sufficient sensitivity requirement, but at the same time that we're keeping that oxide ratio low enough that we can have a really robust plasma. If we don't, and the oxide ratio is too high, our plasma is going to be more greatly affected by the matrix of those samples, and that's where you're going to see drift. So this just kind of gives you a snapshot of, why it's important to really tune your sample introduction system based upon the types of samples that you're dealing with. And the same thing is going to go with your spray chamber selection. So there's a variety of different spray chamber designs, different spray chamber materials, and just like the nebulizer, glass expansion offers some really nice, easy to follow, self-guided flowcharts to make it easier to select the type of spray chamber that's best suited for your types of analysis. So I touched a little bit on a temperature controlled spray chamber with combating drift due to changing temperatures. There's also the actual design of the spray chamber itself that you can consider. So here we're showing Glass Expansion's two most popular cyclonic spray chamber designs. The Twister cyclonic spray chamber, which has a baffle. It's also called a double pass cyclonic, as well as our popular Tracy, which is a single pass or just like an open cyclonic. So the Tracy is going to give you the best signal intensity, right? But the Twister with that extra baffle is going to produce a significantly reduction in the actual volume of sample that's making it into the plasma. So the Twister is actually better for those high matrix samples because, again, we're creating a more robust plasma condition. You're going to get better detection limits and better stability when you're dealing with a challenging sample matrix. Torch selection. So with torches, there's a variety of different models that you can choose from. Most common would be a single piece quartz torch, which you see at the top. Next is a semi-demountable torch. So a semi-demountable torch is just basically the injector is removable from the torch body. Glass Expansion offers a unique and patented semi-demountable torch design with our D-torch. What's a little bit different about the D-torch from a conventional semi-demountable torch is that our intermediate tube is made out of a really robust material in ceramic, and the outer tube itself can be completely removed from the torch body as well as the injector. And then Glass Expansion, to my knowledge, is the only ICP manufacturer that is able to offer a actual true fully demountable torch. A fully demountable torch means that all three pieces of the torch can be completely removed and separate from each other. So you have a removable injector and a removable intermediate tube, as well as a removable outer tube. A demountable torch offers the flexibility of choosing an injector to best suit your application. So we talk a lot about a harsh matrix, right? So typically if you're dealing with anything that's determined to be high in total dissolved solids, you want to choose a larger bore injector because that's going to prevent salting or building up at the tip so that you're improving that long-term stability and eliminating that drift due to the ID of the injector at the tip clogging. Another unique option of Glass Expansion's patented D-torch is the ability to use a ceramic outer tube. Again, another study that I did with Madeline Ghazi from Inorganic Ventures several years ago, again, going back to analyzing these highly concentrated certified reference materials. With a quartz torch, Madeline was seeing a significant drift over time with the standard single-piece quartz torch. By implementing a fully ceramic D-torch, you can see that that stability of measuring those highly concentrated certified reference materials significantly improved. The ceramic material is more durable. It doesn't devitrify like quartz. It runs hotter, so you can also potentially see an improvement in your signal intensity. But because the torch is more robust, you're going to improve your long-term stability because it doesn't have to be cleaned as often because it's not degrading and that material is not embedding within the quartz material because of just the different characteristics of the Cylon ceramic outer tube. General guidelines on choosing cones. So again, depending upon the acid concentration, the samples that you're analyzing, choosing the right cone material can really significantly improve the long-term stability of your results. Copper is going to be the lowest cost option, but it's really not going to hold up to high acid concentrations or harsh matrices. Nickel or nickel plated or having a nickel insert is kind of like the standard all around for everybody. That can be a pretty rugged option. It's better than copper, but if you're dealing with anything that is an aggressive acid or really high total dissolved solid, the best stability that you're going to get is out of a platinum cone. It runs hotter than all three materials, and that basically helps to prevent the buildup of material around the cone's orifice, which is going to directly relate to the stability of your signal. Glass Expansion recently put together a ICP-MS cone resource guide. This is a great tool, not only for shopping for ICP-MS cones for your ICP-MS instrument, but also sort of guiding you as to what material is the best suited based upon your application needs or your acid concentrations. You can scan this QR code or you can visit our website and download this guide. It's really great. It also covers tips on cone maintenance as well. And with that, I thank you all for your time and attention. Encourage you to ask questions with today's webinar. And I will now hand things over to Robyn Goacher, who will talk about her story of conquering drift and improving uncertainty at Materion.
Thank you for the introduction. Just to get my slides up here real quick. All right, so what I'm working on is a high precision composition measurement at Materion. And the first thing I want to do is give you a little bit of information about what Materion does. We have three main divisions and many locations worldwide, and we are a materials supplier for a variety of industries. In performance materials, one of the most popular aspects is that we provided the beryllium and gold coated mirrors for the James Webb Space Telescope. We also do a lot for communications, electronic materials, and we have a precision optics division. Where I'm situated is in the electronic materials laboratory. And one of the things that is of really great importance for us with ICP is to use OES to determine the composition of our metal alloy products. For all of our high-tech applications, the tighter specifications allow our customers to have greater control over their product performance. But what that means for the laboratory is that we have to decrease the uncertainty in our testing. In this case, I'm looking at a two-component alloy. And what was really considered to be acceptable when we compare the specification limits was we needed to at least get below 0.25% of the atom percent uncertainty on what those alloy compositions are. But that's, just barely acceptable. And the real goal was to get us under 0.1 atom percent uncertainty. So for those of you who are looking at percent in terms of like percent relative standard deviation and all of that, this is a top end. It's not a standard deviation end, but it's also an expression of that if you're looking at the composition of this really equates to about 0.2% relative uncertainty on your ICP signal. For the test conditions that I'm looking at in this particular application, I was working with about a 30% composition of the second component of the alloy. With the metals that we're looking at, of course, we're doing an acid digestion and working with fairly high composition on the instrument, about 100 ppm. But we did have to use a high acid percent to keep all of our elements in solution over the course of a lot of runs. We came across the issues of not having enough stability in our data in order to reach those goals for our uncertainty. Even though we were doing a lot of the correct things that Ryan just so nicely pointed out with the internal standard, we also had implemented a bracketing type of calibration to correct for long-term drift just through brute force of mathematically alternating between our unknown samples and calibrants. And to figure out what was happening with our system, we prepared large volumes of the analyte solution, and then we would just measure those, inject them over and over again with our rinses in between for several hours on our thermo instrument. Eventually, what we found out was that our composition was fluctuating with lab temperature. But this was not a polite long-term drift lab temperature fluctuation. This was an evil, pervasive oscillation. And what we had is a monitoring thermometer, and over every 30 seconds, you would see that our temperatures would rise and fall, particularly in the summer months with the air conditioning turning on and off. And the peak to trough differences here are around 5 degrees Celsius, 10 degrees Fahrenheit, and this is not a whole day. This is an hour or two. We would have every 15 minutes or so a full temperature cycle. And when we looked at the injections of the exact same solution over time, you would see that even with the normalization, the internal standards, the bracketing, that we were still getting a composition fluctuation simply due to the fact that the performance of the instrument was changing with temperature. So the ISOMIST and other products that Glass Suspension offer became of real interest to us. And we also were like, well, why don't you just fix the room? Because when you look at the site preparation checklists for ICPs, the manufacturers say, well, why don't you, for optimal performance, you need to have a temperature stability of under 2.5 degrees Celsius an hour. We certainly didn't have that. So we're not meeting that checklist recommendation. And in order to fix the room, it would cost $1 million. So we had to try to find an alternative way of getting to the lower ICP uncertainties that we needed without having to wait for a major capital investment. And what we did was we looked at the sample introduction system. So what we had been using was pretty standard on our instrument. It was a K-type thermonebulizer with their glass cyclonic spray chamber. And I compared that with 4 options from Glass Expansion. These are in order of kind of increasing complexity. The first was simply to switch to the sea spray nebulizer. I mentioned that we're using high concentrations, and so this is really designed for high total dissolved solids. Also looking at their spray chamber, see if we could boost the signal to reduce our noise issues. We did the same thing, adding their Allegra argon humidifier, hoping that that would help us to control the kind of nebulized spray distribution. And then we also added in that ISOMIST temperature-controlled spray chamber. With that, we looked at both a freshly cleaned system and also one where it's simulating, well, what if you're running the same material and you're just, hey, let's leave it set up for a few days in a row. And then lastly, we added the Allegra argon humidifier into the ISOMIST with the sea spray. In all of these, we did make sure that the setups were well equilibrated before the first injection. So what I'd like to show you here, and you can tell there's more data to come, is a distribution of how many of our injections were within the required trueness or bias of our known composition. So this is all injections of the exact same large volume of solution. You can see in this case, it was 29 injections that we did with our basic setup. And it wasn't terrible, but it wasn't what we needed it to be. About a third of those injections landed in our ideal zone of being spot on with composition to within 0.1%. More than half of them, though, were in that boundary layer between it's okay and great, but we did still have a number of injections that were outside of our performance requirements. When we switched to the sea spray, we found that the intensity, the frequency of our ideal injections increased by quite a lot, and that the Allegra argon humidifier also increased. So that helped, but it didn't reduce the fact that we still had a number of our samples that were being run that were landing outside of the appropriate bounds. When we added the ISO-MIST for the temperature control, both without and with the Allegra for argon humidification, you see that that orange bar of unacceptable accuracy completely disappears. I'm also showing you now the two bars. The first at 100% ideal circumstances was with a freshly cleaned system. I have to praise the simplicity of the LUO nebulizer cleaner that Glass Expansion sells. It makes it really easy to clean your nebulizer and to obtain that kind of quality data. However, even when we abused the system a little bit and let it run for several days with our samples, we still got everything within the acceptable bounds. Now, what does that look like? So this is kind of just the distribution of them in terms of worst case scenario. This is the same data. What I'm showing you is the worst accuracy, the worst bias for each of those 5 conditions. So we've got a lot of injections. We've got improvement as we move into adding the sea spray nebulizer. We've got improvement with the argon humidifier. We've got much better improvement with ISO-MIST. And then it seems like the ISO-MIST and the Allegra are pretty much the same. But of course, we also have another technique, which we're all familiar with, which is go ahead and average multiple injections. Yes, this takes more time and resources, but it can improve your data. And you see now if you're averaging 2, 3, 4 injections in a row, especially with that oscillating temperature and composition, you start to dampen out those averages. But it's going to take you 4 injections in a row with our basic setup to get an average that's as accurate as a single injection with the ISO-MIST that's clean, or the ISO-MIST with the Allegra that's clean. So this was a real savior for us in terms of our quickly changing lab temperature environment. Now, the other thing is, well, why would you, how do you decide between these two? And with that, I looked at the precision now. If you're looking at how consistent are those 2, 3, 4 in a row injections compared to each other, even when we had a little bit of a dirtier system, we still had a really good precision with the Allegra. So I found that adding that argon humidification helped increase our precision, the repeatability of this data. And so this is where we've landed for this application. Altogether, when we go back to that original data I showed you with the lab temperatures and what we had initially with very large swings, this was 31 plus or minus 0.2% composition with our basic setup with no temperature control, with a narrow bore nebulizer without argon humidification. And when we added all of those things, then we were able to get a much tighter composition number. The maximum difference there was under 0.1. Our standard deviation was 0.05. There is still a little bit of a response from the instrument because you're really just controlling the spray chamber. It's a very important component, but it's not the entire ICP. But it definitely brought a very challenging lab condition into control for what we needed to get as far as performance. So to summarize, using their components really saved us in terms of getting the accuracy and precision that we needed for our method. And in particular, I think the sea spray was great for our high dissolved solids. It increased a number of injections, getting us into the ideal uncertainty zone on our histograms that I showed you. But the ISO-MIST was the most impactful component for dealing with the rapidly changing room temperatures, particularly in the heat of summer. And finally, I do think that the Allegra argon humidifier is worth the investment as well. It's very easy to use and doesn't have to be refilled all that often. And so altogether, I want to thank you for including me in this and for the expertise that Glass Expansion offered to us when we came into this problem. They're a really great resource for the community.
Awesome. Well, thank you so much, Robyn. I'm going to turn things over to Liv. She is going to give just a quick overview of some stability topics, and then we're going to go into questions.
Hi, everybody. I'm just getting my screen share really fast. So Ryan and Robyn were kind enough to talk about instrument stability. I'm going to be talking about stability of your solutions. Is it? There we go. Okay. So we're just going to be talking about developing a stability program for CRM dilutions. So the benefits of a stability program for CRM dilutions is that you're going to save time at the bench. You're not going to be spending so much time, hand prepping your standards every week or 2 weeks. And you're going to have a lot more faith in those standards. You won't have to validate them as often as you're making, you'll have to validate them as often as you're making them, but you won't have to make them as often, so you won't have to worry about that validation process. Having ready-made standards that you know are stable for a long time also makes testing easier because you don't have to worry about remaking those standards. You're going to know that they're good for 6 or 8 or 12 months or however long your stability studies run for, and then you just have to pour them up and go. And this will also make troubleshooting easier. You won't have to worry about, oh, did I maybe mess my standard up? Is something wrong in my software? Did I enter it wrong this time when I made it? You'll have it made and validated, and for months and months, you'll have confidence in that calibration that you've got. And that'll give you more consistent results as well. You'll know, like I said, that your standard's good, and you won't have to worry about things failing in your standard or things coming up weird in your results, because you'll know that your standards are good. And so if things are looking weird, maybe it's instrument performance or something wonky with your sample. So it'll just make troubleshooting easier. It makes testing easier, and you'll save a lot of time if you do run a stability program. But as with all things in life, there are also some cons. So a stability program is kind of a time investment. It's going to take a little while to get those returns out of that program. So you're going to need to spend the time designing your solutions and designing your study. And you're not going to be able to really utilize the results of that until you've completed your study. So if you want to test your standards for 12 months, you're going to need to collect those 12 months of data to know that they actually are stable before you can start using them for that time period. So it is a little bit of a waiting game, collecting data and everything, but it's worth it for the benefits. Additionally, when you are running your study, like I said, you're going to need to spend time to design your standards, make sure that they're going to work for you. And it is going to require a little bit of additional testing throughout the study, because you're going to need to check that your standard or your solution is still stable for this period that you're interested in. So you're going to need to run it against a fresh dilution of your standard that you would typically make. And it'll just be a little bit extra testing, but it is something to be aware of. It is additional. You'll have to keep up with that data, make a control chart, monitor trends and everything and all the analytes that you're worried about. But once you have that going, it is a little bit, the biggest con I think of a stability program is that it is a little bit rigid. So if you're running a lot of different methods, or you're constantly testing for different analytes, this might not be for you, because for a stability study, you have to know what it is that you want to study, and you're going to want to have a pretty solid method in place, so you're not changing things like your analytes or your matrix or your container materials or your storage materials, because changing any of that will require you to restart your study so that your data is applicable to the solution that you're actually using. Because if you change any of that, then your data is kind of negated, because that's not the same solution anymore. So now you've heard a little bit about whether stability program might be right for you. You're going to want to design it. So you're going to want to know, like I said, you're not going to want to be doing method development and your stability study simultaneously. You're going to want to have everything fleshed out. Being aware of common compatibility issues can really help, because if you know that your analytes might not play nice together over time, you can go ahead and split those out and have different sets of standards that you're doing studies on, and that'll save you time in the long run. You'll know that they'll be stable, and it's just worth it to do your homework a little bit. Like I said, you're going to want to know what you're starting with, so your matrix, what's going to be in there, what are your concentrations, because even changing the concentrations that's a different solution, so you'll need to restart. And then again, you'll need to also know, where's your solution going to live? Is it going to live in the fridge? Do you have the storage space for that? Is it going to live in plastic or glass? Because each of those container components has a different set of issues. So these are all things that you need to have fleshed out before you start your study. And once you know what you're going to be testing, it's important to know how long you're going to be testing it for. We don't really recommend testing or using working solutions for longer than a year because of transpiration, which is the loss of water vapor through the container walls or the opening every time you open that bottle. And this will cause your solution to concentrate over time. But you can mitigate this with refrigeration, but it is something to be aware of when you are worrying about the long-term stability of your certified solution, because that certified value is critical for our data integrity. And again, storage capabilities are important. If this is something you want to refrigerate, you're going to need to make sure that you have the fridge space for large volumes if this is something you want to use for a long time and you use a lot of it regularly. And while you're designing your test, you're also going to want to make sure that you go ahead and set what your pass-fail criteria is going to be. These should be strict enough that they're going to obviously pass your calibration and shouldn't be any looser than your calibration verification, because that's not going to really help you if it's passing your stability test, but it's failing your calibration verification in the future. But you also don't want it to be so strict that there's no room for any variation, because like Ryan and Robyn pointed out, there is some instrument variation from day to day, and a lot of it is preventable if you take care of your instrument, but some of it's just not. Sample prep from different techs can't be really prevented. So these little variations are still important to keep in mind when you're considering your pass-fail criteria, because you don't want it to be so strict that nothing's ever passing, because that's not really representative and it's not really fit for purpose. So like I mentioned, when you're designing your solutions, it's really important to keep in mind chemical compatibility. It's not really feasible if you're running 75 analytes to have them all in one solution, especially at high concentrations. They might not be stable for that long. But it's also, you want to make sure that you're still being efficient and not splitting out 13 different solutions, because that's still going to cause you a lot of work. So if you do your homework and you read up on different compatibility issues, you can kind of set yourself up with a set of 2 or 3 standards that are all your analytes split into different solutions that will still keep each other happy. And it's critical to make sure that running multiple standards like this will also work with your method before you go ahead and do that. We have a lot of resources on our website. This is a screenshot of our interactive periodic table, and each element, if you hover over, has a lot of information about stability, sample prep, storage and handling. There's interference information. So this is a really useful tool when you're trying to figure out what elements you can and can't put in solution together. And we also have a lot of other resources on our website as well. So we have the Ivy Ignite, which is our virtual training academy. We have Bench Boost, which is a podcast where we go through all the sample prep guides. We've gone through the ICP guide. There's a lot of useful information in there. And then of course our website, you can get in contact with any of our technical support chemists and they can help you out as well. And then again, Mike mentioned it, but we are going to be at Pittcon in ICP Alley, and any of the vendors there will be grateful to help you with any ICP questions you have, any solution questions, and thanks for your time.
Awesome. Well, thank you, Liv. And we will go ahead and jump into Q&A. So just a reminder, if you have a question, please type it into the Q&A box, and we will start answering those now. So the first one up is from Julian, and they're asking, when we have a high nebulizer back pressure, what is the best way to clean it?
I guess I'll jump in for that one. Robyn touched on this a little bit. So Glass Expansion has a dedicated nebulizer cleaning tool. It's our LUO. We have 2 different models, one for our glass concentrics as well as one for our inert concentric nebulizers. It's basically designed to safely lock the nebulizer in place so that you can back flush that blockage safely and properly out of the nebulizer. even if you don't have a blockage, I recommend using the LEO regularly, just to ensure that you have a clean nebulizer. I think Robyn's presentation showed a great comparison of, like, if you do a really good thorough cleaning, how amazing your results can be, and compared to, you know, when you start to see that things have been exposed to that sample matrix over a period of time. So that's what we recommend. We have a really great detailed, or almost like a cookbook recipe on our website that sort of walks you through step-by-step procedure as to suggested acid concentrations, suggested cleaning reagents, what concentrations to use, and what sort of steps to take if you have a really troublesome blockage, some additional steps other than, you know, just using the LEO, what you can do to sort of safely and properly sort of clean that nebulizer. The one thing you definitely do not want to do is a glass nebulizer, inert nebulizer. Don't sonicate them. Don't use a wire to stick anything in that orifice. Once you damage the tip of that nebulizer, you're making irreversible damage to its nebulization efficiency. So just make sure, even if you're not using the LEO, if you don't have a glass expansion nebulizer, make sure you follow your manufacturer's recommended cleaning guidelines. But I think everybody's on the same page that, you know, the old school method of inserting a wire into the tip of the nebulizer is really not a great idea.
Yep. All right. Well, thank you, Ryan. Just to let all the attendees know, because we are coming up on the hour here, all of our presenters have agreed to go, 5 minutes past the hour to answer questions. But if we don't get to your question, we will answer it in writing and then send that out to you. So before we move on to the next question, I just wanted to mention that. So if you have a question, please enter it into the chat. If we don't get to it live, we'll provide you an answer in writing. So the next question is from an anonymous attendee. They say, for proficiency samples that have heavy sediment, have you had clients see a change in accuracy by catching the sediment?
I assume this is in relation to either the Guardian inline filter or Guardian probe. No, we haven't. So we've got, when we first designed the Guardian inline filter, we sent it off to several different customers of ours dealing with a variety of different types of samples. One that comes to mind is, mining, where they're dealing with like clays and things like that with really fine particles, and those would wreak havoc on their switching valves, nebulizer blockages. And the answer to that is no. We also have sent the inline filter and Guardian probe to people within the tribology industry, so wear metals, in oil, where you have like metal fragments in the oil samples, to analyze what components of the engine are failing or need to be repaired. So no, so we haven't seen any issues with that. I think the thing to sort of think about is that those heavy sediments, or anything that would have normally been taken up and analyzed, will make its way through the Guardian probe and the Guardian filter. All we're doing with these products is preventing the products that would have resulted in either the capillary tubing or the orifice of the nebulizer actually blocking because of that undigested particulate. So that's just something to keep in mind.
Perfect. Next question we have here from Adrian. And they are asking, a lot of great maintenance tips were presented with the goal of minimizing or eliminating signal drift. How does that maintenance help with intra-run drift? So not from one run to a separate run, but drift within a run. And they're saying that's their problem, not run-to-run changes.
I'm happy to jump in again, but I don't want to be the one that's answering all the questions. But maybe Mike and Robyn can piggyback, or Robyn, you take this one.
Yeah.
For me, I feel like, definitely you should be using an internal standard. One of the biggest issues that I've had within a run, if your repeats aren't good, is to really focus in on your sample introduction system, in terms of is your, change out everything from your sample probe through your capillaries, make sure that your nebulizer is clean. What I learned from my study is just how important the repeatability of that spray of the nebulizer is. If you're not operating under the right conditions, then you can really get an improper or inconsistent droplet distribution. And that'll make small changes to the temperature of your plasma, and that'll make small changes to your ionization efficiency and how much excitation you're getting too.
Yeah, great. Next question is, do you provide customized multi-element ICP-OES standards CRMs? Yes, we do. So if that is your question, please reach out to Inorganic Ventures and we can provide you a customized standard for just about any of the elements that can be analyzed by ICP-OES. I think this one is going to be specific for you, Ryan. Are the components compatible to all the big brands, or is it brand specific?
Yeah, I should have mentioned that. So glass expansion manufactures consumables, accessories, tools that are compatible with every major ICP manufacturer on the market. You can find many of our products within those instrument manufacturers' catalogs. You can find our products. You can purchase them directly from Glass Expansion. You can find them with your big shop laboratory supplies. At the end of my presentation, I listed our 3 offices. So we have global support. We have our main office in Australia. My office is in Massachusetts, and we recently opened an office in Germany covering Europe. And all of our offices have an extensive distributor network so that we can expand our support all around the globe. But yes, so whether you've got a Agilent, a PerkinElmer, a Spectro, a Thermo, Shimadzu, we make sample introduction components for every ICP instrument out there.
Perfect. This next one I think is for you, Robyn. All of the drift values based on the previously mentioned method, including bracketing and internal standards, and just changing to new components. If that's the case, why doesn't the mentioned not catch the fluctuating temperatures? So I think that's why, if you're doing the internal standards, why is that not catching the temperature fluctuation?
Yeah, so that's a really great question. So to clarify, all of the data that I shared with you today did use internal standards and bracketing, and the only thing that changed were the hardware components for the sample introduction. I think the reason why the ISOMIST temperature-controlled spray chamber was the really important aspect to the change is that aspect of having a really consistent nebulizer spray droplet distribution. And that helped us to control and keep a more constant size of particles that are entering into the plasma, which really controlled, again, what's happening in terms of line intensities. Ryan may have additional aspects to share with his research from within his company too.
Oh, sorry. Yeah, so I think the other thing with the fluctuating temperature, right, especially with ICP-OES, is that whether it's an atomic or ionic line, they all are going to behave differently at different spray chamber temperatures as well, because the fluctuation of the change in the temperature of the spray chamber is also affecting the transport efficiency of that aerosol to the plasma. So some atomic or ionic lines that are easier to ionize and atomize versus ones that are more challenging, they like different conditions. And that's what's sort of tricky too, is that oftentimes you have to find the balance or the sweet spot, right, and that's also where it's important to choose the correct internal standard lines to monitor the elements that you're looking at to make sure that they're matching the behavior of the elements of interest. So if you take a look at the ISOMIST landing page, again, I mentioned that, Robyn's application was strictly to eliminate that temperature drift, that variability, but you can also use the ISOMIST to increase sensitivities for certain elements and certain lines or improve accuracy. If you're looking at, we had a nice study on precious metals where they were just looking at a certain suite of metals and they could fine tune the temperature of the spray chamber to really improve the transport efficiency and the measurement accuracy of those specific elements. So I think that's the other tricky thing too, is how those elements, those wavelengths, sort of behave in the plasma. So that could also be, something to keep in mind.
Yeah, that's a really good point. And just real quick too, we were plagued by the issue that the internal standard really helps with a different amount of sample uptake. That wasn't really our problem. And then the aspect of the bracketing helps much more with long-term drift, like a gradual drift in temperature. But we would have maybe 2 injections within an upswing of the temperature. It wasn't enough to do a full bracketing cycle. So the bracketing helped, but it wasn't able to really be the right match of how fast the temperatures were changing on us.
Yeah.
Great. I'm going to say let's try to get 2 more knocked out before we close it out. So if you do have a question, like I said, we will be happy to supply answers in writing shortly after the webinar. But let's tackle these last 2 questions because I think they'll be relatively quick. This one coming in from Juan asking, well, it is true we do offer, so IV does offer custom standards in 20-liter jugs. He says, however, no transpiration study has been made publicly available. If he recalls correctly, there's a relationship between the size of the standard container and the geometry of the opening. And then he goes into detail saying, the jugs that he has are not open directly, and the solution is accessed through a spigot. Any comments? Would this solution be good for longer than a year? And Liv, I'll turn this over to you.
So yeah, there is a relationship between the size of the standard container and the opening. The smaller the opening compared to the volume, the less transpiration happens. But transpiration is still happening through the walls of the container as well. And I think in our case, our cert says, once you open it, it's only good for a year. So I wouldn't be able to say, yeah, you can use the 20-liter longer than that. But for your own studies, if you were to prep standards in your lab, I would think that, having a smaller opening compared to this larger volume container would definitely decrease transpiration. And if you were to do that study, you could get longer than a year of working time for solutions that you made yourself. But again, on our cert, it says that, so I can't really say, yeah, you can use this longer than that.
Yep. So we've done a few transpiration studies on larger size containers, and without opening them at all. Once you get above about a 5-liter QB, if they're all sealed up tightly and not open, the transpiration is very little. But once you start opening it and creating headspace within the container, that's when you'll see transpiration start to increase. And I will say later this year, we will have more detailed usage studies for transpiration rates in our regular size bottles. There are some high throughput labs that order their custom or their CRMs in larger containers, but most folks are using bottles, and that's going to be something we'll be excited to sort of go through later in the year. We had a study finish up late last year about real world usage rates, so you can see the relationship between that headspace and the transpiration rate. And then the last question I want to get to before we close off is from Heath. At what temperature would you recommend baking quartz torches and alumina injectors to remove organics?
It's a great question. I don't recall the exact recommended temperature off the top of my head. So if Keith doesn't mind, we'll write up a response to that so that I don't tell anybody the wrong temperature to use and cause irreversible damage. So I think I know what it is, but I would much rather ask the folks in our R&D lab to confirm what I would say.
I know. I think I've got a number in my head as well, and I'm like, it's either right or it's gonna melt something. So I would much rather look it up.
Yeah.
All right. Well, if you are still in attendance, and it looks like there are a great number of you still on, thank you so much for letting us run over a little bit. We really appreciate your time. And like I said, we will supply the answers to these questions in writing. So check your emails for that. And I hope you have a wonderful day. And thank you to our guests today. Thank you, Ryan. Thank you, Robyn.
Thanks, everyone.